work. I had this set up with Bluetooth mics and I tested it, but her demo doesn't have a sound, which is very unfortunate. She made a huge effort to come from Canada to New York, especially for this. I really appreciate that. So let me open the Q&A. I already shared in the chat that according to Cloud Skill Boost, today's courses, there are two of them, but they take 3 days. So if you're ahead of the pack, that's fantastic. If you're not, please make time for this. I know it's summertime, but I don't know. I'm super excited about the fast pace that this field is moving. I know we're focused on Google Cloud, so they literally made available the Imagine or the image generative AI studio image became in public preview literally a couple days ago. So definitely this field moves very fast. So I wanted to share the links for this week. And I hope all of you are on the tracker. Thanks again for sharing your Cloud Skill Boost profile, and thanks again to Roman, who is the GDG Lawrence and GDE Flutter and Cloud Architect who has built this for many GDGs, including us. We officially have 80 learners on the tracker, which is by far the most any GDG has had. So that's very exciting. I shared the Cloud Skill Boost. One is called Computer Vision Fundamentals with Google Cloud. And the other one is called Production Machine Learning Systems. That's the one that takes 2 days. Who wants to share their progress and how far they are? Does it take less than 2 days for you? Mari told me something that takes 6 hours took her an hour. If that's you, also more power to you. So, any questions, updates, exciting stories, or everybody is just waiting to begin? Paul has a question. What do you mean by 18? You can use your mic if you want, or um, camera even. Um, are you saying there's a problem with that lab? I mean, that's like a
I,
course.
I've been told I've get halfway through it and it fails out, and I've been told that they're having an issue with it, and I was just wondering if they'd gotten it fixed yet.
So there are a few video. Do you mean particular one? There's literally like
The labs,
I'm not aware of any problems with that, but if you are, can you be more specific? Which lab?
Uh, Classifying images with a linear model.
Because the link you send goes to the entire course, so I'm not sure which lab you're addressing. Lab 3. Is there a link to that lab? Or as far as I know, there was an issue with a lab that we have removed from the learning journey. That was for the previous week. One second, let me check what that one was. So, explore machine learning models with explainable AI. That was something we removed because there was a problem. I think that one. I mean, that one is doesn't even, there's no, the link doesn't even work anymore, so it's been taken down. Um, the one for, the computer vision fundamentals, as far as I'm aware, there's no issue. But if you send me a direct link, that would be helpful. Although, are you talking about the same lab? Honestly, if you send me the link, there's hundreds of labs. I don't know which lab is 381, but I'll definitely can check that for you. Um, so yeah, I mean, if there's 2 days of uh, things that need to be completed, then don't get. I mean, move on. Don't get stuck. Oh, fantastic! Thank you for that link. Um, One moment, I'm checking. I'm not sure why this. Can you share your screen, Paul, what you see? Because I don't get to a lab when I open this. This link you posted, it redirects for me and I can see what you're talking about. If you want to share your screen.
Are you seeing it yet?
No, I cannot. I literally cannot open this link. How'd you get to it?
Uh, from the, uh, are you not seeing my screen?
I'm seeing your screen. The link that you shared redirects to Cloud Skill Boost and doesn't go anywhere,
Uh,
which is very weird. Even if you're signed in or not, you should be able to get to the lab, right?
uh, I'm signed in. Yeah, you have to enroll in the course. Um,
Which course is this part of?
the vision, the computer vision fundamentals with Google Cloud, which is one of the ones that were on the learning journey for. Oh, that's for the next 2 weeks. Next week.
I am enrolled in it, but I don't. The link doesn't open for me.
Huh. It goes. I go right to it.
I mean, I guess I'll save the. It
This.
literally redirects, and I says sorry,
Okay.
access denied.
Okay. Computer vision
And I have all the
fundamentals.
credits and everything, so this is extremely weird.
Right.
Um,
Computer vision fundamentals with Google Cloud. Okay.
yeah, I am enrolled in that.
And then let's see. Which one is it?
Oh, so always sending another link.
I do believe each link is unique to each user. That course sessions is a unique identifier for that user logged in to Quick Labs at one time. The number after labs is unique to the lab, but the number before labs after course sessions will not work for another.
Oh, are you saying there is no public lab link to that lab?
I do believe the course sessions is unique to each user. So therefore one user's course sessions, one user's link will not work for another user.
Okay, so Paul, if you send a screenshot of the lab, then. But as far as I know, you can send the public link to a specific lab.
I think the lab number is the 6 digits at the end. It's 381961 because my link looks like Paul's, except the number before the labs is different. Like the other person said, the number before that is your identifier.
Okay, so there's no way to um, there's
I
no way to
agree. Yeah, there is
get
no
to
way.
that lab without personally being
This
signed in.
lab right here.
Yeah.
It's in. It's in the third. It's in the custom training with linear neural network and deep neural network models.
Okay. And then?
You go to that lab, and I've talked to support several times. They keep telling me the lab has a problem and they're working on it, but I've been working on it for a while.
One second. So the lab that you and Olu are talking about are different though? Olu, is your lab the same one as Paul?
No, mine is let me confirm mine is introduction to linear regression. Can you hear me?
Yes.
Okay.
So I guess the way to go is by the lab because the session prevents having a common link. So I've taken note. So no one has passed, because I saw that some people have already completed those. Has anybody completed these?
It's under machine learning in practice.
I'm sorry?
This lab is under machine learning in practice.
Oh, so it's not from session 4. From which session it is?
That should be, I think, 3. Let me see.
Now I am signed in, and I get a message that classifying images with a linear model is currently unavailable. So I'm not sure why I cannot access the lab at all.
Well, that answers the question, doesn't it?
That's weird that some people have access to it, some don't. I mean, I am signed in the course, and I see it as I see it listed, but once I try to start it is not available. So good catch, I guess. I guess don't do that one. I'm not sure if if you enrolled at certain time. Since when did you try to do this? Paul, you said you contacted Quick Labs.
I'm sorry, what?
You said you contacted the Quick
Yes,
Lab.
I've sent them I've sent them so many emails, and they keep sending me back that they're working on it, and they'll let me know. And I got a notification on one of the labs today that it was supposedly working, and I tried it. It failed again, so I'll just keep bugging them.
Oh, you're talking about a different one?
I've got several ones that are going that they're failing, and Google Labs or Quick Labs is telling me that the labs are not available right now. So I'll just keep waiting.
Oh, Rich is ahead. I'm just reading this. We are the QAs for the labs. Good one. I mean, I can contact there is another place to contact. And it is, let me get the email for that. One second. Um, GDG support at google.com. Have you contacted? Um, GDG support at google.com is another one that I have very good record with. Not for the labs, but getting access and all that. But they're another resource for you to contact if you want. I personally am planning to contacting them there. So, but basically, let me share the tracker once again. So, is everybody on the tracker, by the way? The batch tracker? And if there is issue with the lab, we'll definitely here's the batch tracker. Please make sure your name is on there. And we can definitely add you. So you get notified that the labs are, how do you get notified? By email? Oh, cool. All right. Oh, fantastic. Great to know. Yeah, I also use the chat in the labs too. They usually reply pretty fast. So let me check where our speaker is. One moment. Any other questions? Okay, so Maddie's coming any moment. Let me open the Q&A is open. There's another lab in the Q&A which does open. Has anyone had problems with this, with the Vertex pipelines? Oh, hi, Vulcan. Vulcan is here.
Yes, Anna. Hello. Thank you.
Always great to see you.
Thank
I
you.
love our international
Yeah.
learners from other continents. So there is a question about that lab as well. I haven't heard any problems with the Vertex AI. Fantastic. So, okay, so thank you again for your patience and that you are well versed in going through the labs. I believe our speaker should be here. Oh, Maddie, she's already a host and everything. So we have a lot of material to go through, so we can get started. So Maddie, please, you have the floor. You can share your screen or speak or camera, whatever you wish. And thank you for joining again. I'm really looking forward to today's questions and quizzes and overall material.
Okay, folks. Do we have audio?
Yes, we can hear you.
Oh, okay. Yeah. Sorry about that. It's my first time kind of like doing the presentation, therefore had a little bit of a struggle with the platform. So how are we the labs? I know Anna, you were probably just checking with folks.
Well, there are a few issues with the labs that I've taken note of, but sounds like Quick Labs is aware and
Okay.
yeah.
Because
So
we
I
can't
take
really
a
like.
note and I'll follow up with GDG support. But if Quick Labs are aware and they're not working, we should remove them from the learning journey. But I wasn't aware that there are any issues with
Okay.
section 4. But some people have completed them, but as time goes by, there could be bugs that appear. So Paul is the most active one. That
Awesome.
I'm not sure if you can see the chat, but
I cannot, and if there are questions, because I cannot see the chat, usually I'm like watching the chat to answer questions. You may need to kind of like ping me for that, if
okay.
that's okay.
Well, I've taken note of the labs that are not working, but
Oh, I
going
mean
forward,
specifically for the
we
content,
have
yeah.
Q&A. So if you have questions during Maddie's presentations, please post them in the Q&A so they stand out.
Yep, and
But
I
yeah,
think
so
what we'll
far
do is
there are 3 labs that are problematic, but today's questions should be in the questions tab.
okay, awesome. So I think we'll just get going then. I'll enter slideshow mode. Are we seeing the slides? No? Let me know if the slides are up.
It says loading.
Okay. Yeah, apologies. This is, sometimes we have platform. isn't, so we will see how it does. Okay. Is it still loading or?
Oh, now you can see
Okay.
it.
Okay, awesome. So we are now week 4, and I am not Roya, but I will kind of lead you through the rest of these sessions. Obviously, we'll still have office hours and all that. So blank slide. Where are we on our journey? So we kind of went through most of the basic stuff, and now is where things get like really juicy. For example, some folks are probably interested in deep learning, and there wasn't too much of that, but from now on there will be a lot of kind of production focused, and we'll get to do some of the cool things like, you know, image related, like computer vision related machine learning and all that. And I'm especially excited about next week because we're going to be learning about NLP, which is basically the broader field of like all the large language models and all that exciting stuff. And also because time series have a sequential nature, models that typically work well in language tend to work well on sequence and vice versa. And also recommender systems and all that. Let's just focus on this week for now. So this week we're doing the cool stuff. Like when people talk about being a machine learning engineer, this is kind of what you're imagined. But as Roya probably, hopefully, you know, impressed upon you, until your data is good, none of this is going to work. So definitely focus on the data. But if you did go work with your data exploration and data cleaning and data processing, and you have your pipeline set up, now you know all that hard work. Now you get to have fun. So this is kind of the part of the process we're going to focus on from now on. And let's first talk about underfitting versus overfitting, right? This is probably the most standard chart I've seen about how to explain this, but the way I think about it is that overfitting is your machine learning model has remembered the data instead of learn how to generalize. It didn't learn to reason, it remembered the test, right? There's actually some debate and even hypothesis about what exactly is a large language model doing, right? Is it actually learning things or is it remembering things? Because, you know, it's entirely feasible as models get bigger and as we add more parameters, if you internet, it will just remember most of the things. And therefore, when you ask it, oh, you know, who's the president of United States in like 1982 or something, you will know the answer. Is it because it knows the answer or is it because you remember the answer, right? So overfitting is kind of the most extreme example on the right-hand side. And then let's talk about the other side, and then we can talk about the happy medium, right? It's underfitting. Underfitting is when your model actually doesn't remember, it doesn't have the capacity to figure out the patterns in the data, right? So this is typically when we say that a solution would be to add parameters, right? So hopefully so far so good. So then let's talk a little bit about how do you know if your model's doing underfitting or overfitting, right? So if you're looking at a simple example in the case of regression, this is a pretty good way. If your line has too many like squiggles and you as a human can pick out a general pattern, then that's probably overfitting. And if your kind of like model is very simple, it doesn't kind of like follow all the bands or patterns in the data, that would be underfitting. So your human judgment and visual intuition is actually a very good guide for this, right? So let me ask you a question. Like, if you had to err on the safe side, would you rather overfit a little bit or would you rather underfit a little bit? And why? So this is a question for the group.
I'd rather underfit than
Do
overfit.
we have any like guesses as to if you had a choice of like say overfitting by a tiny bit or underfitting by a tiny bit, which one you would prefer? And feel free to answer in the chat. Okay, seeing lots of like votes here. Good stuff. Awesome. So I'm going to pick on the odd one out, because either they will like bring everyone up to speed, or we may get to like learn something new, learn new like interesting perspective. So I'm probably going to mispronounce your name. I'm sorry, but the last person that commented, I'm gonna say Ferenc. Would you be interested in like either answering in the chat or speaking up on the call to explain why? Okay, Vulcan says, it depends. That's a good answer. Hello, do we still have audio? Okay. Awesome. I think Anna just muted herself, so I heard a little change of audio channel, so I was a little bit worried. Cool. So I didn't hear any responses. I don't know if this person wants to speak up, but it really does depend, right? When you're picking a model, especially a deep learning model, you want to make sure like it has enough capacity, and then you can regularize it to kind of like reduce your model size, right? But let's talk about like what exactly is the problem with overfitting in general. Well, overfitting has the problem of like having too many parameters that are not useful, and also not generalizing well, right? So in my personal like workflow, what I typically do as a larger model is that I first run a small data set through the model to make sure it has the ability to remember the information in the data set. And then I will kind of give it the rest of the data, because now the data pattern becomes more complicated and there's more detailed patterns that it needs to pick up. And make sure it is still learning. So that's when you kind of watch the accuracy, and then make sure your training accuracy is kind of like improving, or your loss function is decreasing as you would expect. And then you would then look at the divergence between the training and the data, the training accuracy, and also your training accuracy, and also your test accuracy, right? So this is why we do need to have a training set and a test set. Actually, in most standard practices, you have a training set, you have a validation set, and then you have a final test set. It is best practice that nobody sees the final test set after it's being kind of like sampled. There is this thing that happens called kind of like leaking data by engineer, right? Leaking, right? As in like you somehow have seen the test data. Therefore, when you're doing the model optimization, you are kind of slowly making the model perform in favor of the test set. But in case the test set isn't exactly a good sample of the general distribution where this data is generated, then you would have done your model a disservice by doing that. So hopefully that's good. A lot of people are also saying that it is expensive because model used to overfit are more complex. Yep, exactly. However, compute is getting more and more like lower cost. So it's very easy to do what I call like sloppy machine learning, and basically get a model, get a bunch of data, hit run, and see what happens. But like people said, it's not efficient, and also we could do better than that. Like, that's why we're here, right? Cool. So are we pretty good on this concept? Do we have questions about this? Yep, data swimming bias, exactly. And we're all human. We all want our models to do well, of course. Okay, so I don't know if many of you remember the form I made you fill out, but I'm going to share a link here. So in the kind of like the middle part of this form, there's questions about like overfitting, underfitting, and learning rates, right? So we can hopefully I'll answer these questions now, and we can kind of like discuss that, go over the actual like answers to those questions if people are interested, a little bit later on. Okay, cool. So back to the slides. The slides are no longer following my keyboard. Okay, cool. So if you have a overfitting situation, right? Like we said, this is when the training loss and the validation loss start to diverge, right? What are your options then? Now, obviously, the options are regularization, right? So regularization, you could use L1 or L2 or dropout, and there's a bunch of other options. But the whole goal is to reduce model complexity, make some of the weights actually go to zero, so they don't actually apply in the computation. As we know, if you multiply anything by a zero, it turns into a zero. And in the multiple layers of the neural network, if you have a dead neuron earlier on, then the subsequent neurons who's getting input from that neuron also do not activate, right? Because 0 multiplied by 0, no matter how you do it, it's still going to be 0. So this is how you essentially reduce model complexity. Do you folks know what is the difference between L1 and L2 regularization, and when you might want to use one versus the other? And do we all know what dropout is? I'm not getting a lot of responses. Okay, so people do know. That's awesome. So, William, would you be interested in explaining what is the difference between L1 and L2, and when you would use one versus the other? Okay, cool. So maybe I will do that instead. So I'm trying to find a nice visualization for you. But one of the main properties of L1 regularization is that it actually forces a lot of the weights to be actually 0 instead of very small, which is what typically happens with L2 regularization. So why would that be, like, favorable, other than just reducing model complexity? Having like weights that are 0 are obviously more efficient, because once again, the computational properties of like neural networks and multiplications, right? But also, if you're using regularization, it actually has the ability to do feature selection. So here is a pretty good diagram of what's actually happening, and I will share the link with you. Give me one sec. Okay, so if you look at that graph, it kind of do the overlay of what is the kind of parameter space versus what is the kind of the feature space, right? So if you look at the contours, what's happening there is that we're essentially doing gradient descent on some sets of parameters. Call it, parameter 1, theta 1, parameter 2, theta 2, right? Now, if you have a L1 norm, and L1 is actually just another name in mathematics for absolute. So if you remember what the absolute value function looks like, it basically looks like a upside down triangle with the kind of the tip pointing towards the origin, right? And then because that's the shape of that function space, or that parameter space, it is more likely that your gradient descent will kind of tangent onto the parameter space, where it is either theta 1 is 0 or theta 2 is 0. Therefore, you have eliminated essentially one parameter entirely, right? So then if you look at the L2 regularization, it is more likely that you kind of intersect towards a small value. All the values are still going to be close to the origin, but it is not 0, as in it's not intersecting on the axis, right? So this is the main difference between L1 versus L2 regularization, and one of the ways you can make this choice. So the caution with L1 regularization is that, because if you're using L1 regularization for feature selection, and if some of your features are like linearly correlated, it doesn't always pick a reliable favorite, right? So let's say you have two variables that are highly correlated. I'm just gonna, name some random things, maybe like, obviously, like major generalizations, maybe like your age and your height, right? As you know, when you're building a regression model, or like a simple regression model, you prefer the features to be like linearly independent. And obviously, we know there's some kind of dependency between your height and your age. And then so when the L1 regularization is happening, there's a good possibility that it puts a weight of like 0.8 in front of your height, and then puts a weight of 0.2 in front of your age. And let's say you're trying to predict your income or something like that, right? And let's say you'd run the model another time, it may not keep those weights like consistent, right? So that may produce like model instability kind of issues. But in reality, if you're working with a lot of data on a very large model with a lot of parameters, for example, deep learning neural networks, this factor matters like less. And dropout is essentially when you're doing your training passes through the model, you artificially turn off some neurons, right? So why is this good? It's basically reducing the ability for specific neurons to remember things instead of like picking up the general patterns in the data. And this is also like a little bit like adversarial training. So let's say you're a doctor and you have a bunch of like surgical tools, and to kind of like improve your skills or make you actually learn how to do the task and not just remember the task, I may just like take away one of your tools and make you like be creative and figure out how to do the the process with other tools, right? So that's kind of like equivalently to what is happening in dropouts. When we talk about computer vision, dropout is actually very important, so we can like expand a little more on that. Yep. Okay, so underfitting. Underfitting is when you see like kind of your loss and epoch chart that looks very close together, and usually it's very flat, right? So in the previous chart, we know the model is actually learning stuff, and one of the key indicators that you see that very steep drop from the beginning, right? So if you're not seeing that when you're training your machine learning models, usually what I like to do is print out the loss or like graph it as it's progressing in training. If you don't see that dropping loss in for your training set, or if you don't see that kind of like increasing accuracy for your training set, then something is probably wrong with your code, with your model, because your machine learning model is not learning anything, right? Regardless, you're better off just stopping training right there. So that's kind of like what's happening here, right? So the model's not learning, and also your training loss and evaluation loss or test loss or validation loss is like incredibly close together, right? So this would be consistent with a model that's kind of like randomly guessing. Like it doesn't know the relationships in the data. It's not capable of learning it, and that's pretty much what happens. So what are some of the ways we can like decrease underfitting? Actually, one of the easiest ways is to add model capacity, right, or model complexity by adding more neurons, adding more layers. If you're working with like a simple regression model, adding the power of exponentials, right? So a linear regression, people think a linear regression cannot have exponential terms, but that's actually like a little bit incorrect. You can actually add exponential terms in x, for example, x to the power of 4 or 5 or even higher, to a regression model considered linear regression, because the relationship between the powers of x are linear, right? But if you experiment with this data and you add the powers of the x, what you will see is that essentially you're increasing the model's like expressive capacity, and therefore you will see kind of more squiggly lines in your kind of like your final model. So if we're going back to that regression example, it will look a lot more like the final graph, right? So there is that. So we're at a breakpoint with the kind of overfitting, underfitting diagnosis content. Do we have any questions? Yeah, one pointed out something interesting. So L1 is absolute versus L2 square of error. So L2 has a higher penalty of outliers. Yes, that is accurate. So let me show you a different way of looking at this. Some people are more visual, some people are more how should we say, more like, I guess, textual learners. So maybe this will help. So let me get this image for you. Yeah, this is what I want. So let's look a little bit at this formula here, right? And this is the breakdown between the regularizations. L1's on top, and as we already discussed, it is a penalty applied to the absolute value in the error, right? So there is a parameter in front, and that is the regularization rate. And so in the L2 regularization version, if you have a large difference, the penalty is exponentiated with a power, right? So, but if you have a like kind of like a small difference, like what happens if you take like 0.2 to the power of 2? It actually becomes very small, right? So the behavior is a little bit interesting if the difference is very small. And if we have a small difference, we probably don't care. So this is why L1 regularization works, and L2 regularization also works, but like used differently in different settings. Okay, awesome. do people like kind of understand how to diagnose learning rate issues? Like, is your learning rate too high or too low? Because that's another common model diagnosis task that you will need to deal with. And then the other one is obviously batch size. I'm using batch size for regularization. I don't know if there's like any like interest in going through that. Okay, not seeing a lot of. Oh, okay. There's two people interested. Okay, so let's talk about that. I'm actually just looking for a good visual so I can explain this better. Okay. By the way, are the links I'm sending to the are the links I'm sending to the chat working for folks?
Yes, I can see them.
Okay, cool.
Only
All
the
right, so
form, Maddie, I think is not
corrupted.
the one that people fill out, but like the admin view.
Oh, okay. So yeah, feel free to share the like one. Make sure we're not leaking data. Okay. So learning rate, right? What exactly is learning rate, and what is it doing? It's do folks have like a good understanding of like learning rate and deep learning, or should we just like go over that real quick? I mean, I see one yes. Okay, there's two requests. Okay, for that I'm gonna share a different slide deck. Okay. Bear with me for 1 sec. Okay, so I'm gonna do a slight change of process here, right? If I mention a topic, I don't want to go over things that people already know, because I know there's like machine learning engineers on the call, but I also don't want to like skimp over it if there are beginners, right? So why ask if people want to go over a topic? Like, really would appreciate you voting. So if you want to go over it, it'd be beneficial to you, then give it a B equals thumbs up. And then if you don't want to go over it, give it a P, means thumbs down, right? This is like honestly trying to this is honestly trying to like do a vote thing and not have people be like upset or shy. So if you don't want to hear it and I don't see your vote, my apologies. Like I only look at the votes, right? So far it's all like upvotes. So if you don't want to listen to it, definitely 100% like vote. Okay, so let me quickly bring up the deep learning crash course. Sorry, looking for slides from previous presentations. Sorry, for some reason, while I'm presenting, everything just incredible. So please bear with me. Thank you for your patience. Okay, let us do this now. Okay. So, don't mind the title of this slide deck. I am waiting for it to load. I'm gonna stop sharing for a second until it loads. Okay, and I will reshare my screen. Okay. So this is starting from the very basics. We're gonna go from linear regression to essentially like the basics of like neural networks, right? Okay, so line fitting, we all know what this is. So basically, if you're thinking about the regression example, you're literally like plotting a line of like y equals mx plus b, right? As I mentioned before, if you wanted to make the model more expressive, you can say y equals mx plus, t x squared plus b. So you're adding extra exponential term in your regression, right? So what would you expect? Well, if your linear regression is literally a straight line, your quadratic regression will basically have curves, right? And if you have a higher degree polynomial in your regression, for example, y equals m x to the power 8, and then power to the 7, power to the 6, whatever, then you would expect a very squiggly line, right? So when that happens, what you will see is that the model will try to go from each data point or each cluster of data point to the next cluster, which is not necessarily what we want. So there's that. So then let's talk about what is the best fit, right? So we just talk about, okay, regression is like learning line of like best fits. What does best fit mean? So this is where we have to define error, right? This is the unregularized error, but if you look at the formula that I was just sharing earlier, you will see a lot of similarities, right? So basically, we're taking the vertical distance of the red dots and then your prediction, which is what your model thinks the data should be, and then we're squaring each of these like distances. So why are we squaring this? It's because some of these error bars actually add up, right? So 15 minus where the prediction is, that's going to be a kind of like a positive difference. And if you take the real data point, say the second data point, 5 minus 10, that's going to be another difference of 5, right? So if you don't square this, the positive and negative errors will cancel each other out, and then you're like, oh, my model's perfect, and then it will not be the case. So don't be sad like that. So once we have by basically taking the difference and squaring them, then we can add them all up, right? So if you only have a few data points and then you have a line to fit them, the overall smaller distance between everything, the better, right? Okay, cool. So this is probably a review for folks. So now we're gonna go from what you already know to like basically something fancier, which is plane fitting. It is literally exactly the same thing, except now x is no longer a value. It has maybe like a few additional coordinates, right? So in this case, x now has 3 dimensions. So if I were to pick a point, I can say x is like 0.5, 1, and then 1.4, right? And then therefore your y is also a vector. It probably also has 3 elements. So what happens is your matrix, your weights from before, or basically whatever m is, previously that is a number, right? But now because x is a vector, w is now a matrix, right? You will hear the word matrix multiplication over and over and over again in deep learning, and especially later on when we talk about distributed training, it's actually very much having to do with this multiplication of your data, which is x underscore and your weight matrix here. This is probably like one of the most expensive calculations in the entire process. Okay, so basically what you're doing in your network is literally just a lot more regressions chained together, and I will basically map the equivalence for you, right? So b is the intercept. Well, we have a like a 1 at the end for kind of to account for that, and then the rest of the x's, which is now a vector, is your data, right? And then your weights are basically here, right? So this is the graph of one single neuron, and then obviously after we have the weights applied to the data, then we kind of add them just like we did before, and now we have an output which is the predicted value y, right? But then the only difference between what we were talking about was plane fitting and regression is that previous neuron actually gets fed into the next layer. And depending on how densely connected or sparse your network is, it is actually fed into potentially every value in the next layer, right? So as you can see, there's a ton of like matrix multiplications. So I'm gonna skip over nonlinearity, and then we can talk about that later if you're interested. So we can also skip over universal approximation theorem. A lot of people are like, okay, so how does increasing model capacity make the model able to learn more things and perform better, right? So there is a theorem called the universal approximation theorem. It's basically about how you can get arbitrarily precise answers or arbitrarily precise answers for almost anything if it's continuous, if you just add more parameters. And for people who are more visual, this is how I explain it, right? So people have probably played around with this pin art before. If you have only 4 pins, you probably won't get a very high def model of this, child's face. But you had like a billion pins, and they're all fitted in that little square. Then you can have way more detail in terms of your ability to represent the reality, right? And reality has like infinite levels of like detail. Therefore, this is why usually adding more parameters will help you approximate whatever process or pattern in the real world a little bit better. So this is also why when you see the advancements of large language models, a huge part of it came from adding parameters, right? Because once again, we think compute is cheap. Okay, so I'm gonna take a quick spin back to the chat to make sure like are people still doing okay? Like any questions so far? Or is this like too boring for you? We should skip? Thumbs up, thumbs down. Okay. Okay, so far so good. Please do share, negative feedback. I'm just here to improve, learn with you, and try and like help out as much as possible. Okay, cool. So so far we're probably like already have a headache, but now we're getting to the cool part, the learning rates, right? So how does the model actually learn? We know it can like learn to represent the real world. So how does it work? Starting with nothing, right? Absolutely nothing, knows nothing. So maybe you initialize your entire neural network with values of like 1. So here's a fun question. Why initialize all the weights in your neural network to be 0, right? For people who are like paying close attention, you will know the answer. Yeah, so trick question, bonus question. How why should you not in neural network with all weights of 0? What happens when we like multiply 0 with other? Yeah, exactly. So if you do that, basically your network just like won't learn, and you will have that very sad like 2 flat lines later on. So feel free to try that if you're not convinced. Okay, so let's say we initialize with something like stupid, right? Like just 1. And then we're like, okay, go learn the pattern. How does it actually do that, right? So machine learning is about taking small steps in the right direction. So at that point, we have to kind of talk about like what does it mean the right direction and all of that, right? So this graph is a little bit confusing to look at because it has like too many moving parts. But let me briefly explain what's happening here. So on the I think the right hand side, you have what we call the error surface, right? And why I think about machine learning, like the analogy I like to give people, just for like a sense of intuition, or if they're new, this is how like I help a visual person think about this. So the goal of machine learning is that you get dropped somewhere on the kind of like the error surface, right? Your goal, because errors are bad, you're trying to go to where the errors are the lowest, right? So what you're seeing, the little ball rolling up and down, is very similar to if you dropped a giant boulder on top of a mountain range, right? It's gonna slowly, depending on where it got dropped and the curvature of the slopes and everything is kind of like moving on. It's gonna go into the lowest pit, right? But it's gonna follow a certain path. It's gonna roll in a certain direction. So far so good, right? But what is the surface? What is the surface moving along, right? So for example, if you look at the axis on the right hand side, dyslexia, apologies. You will see a value for weight and a value for bias, right? So for now, this is actually just a y equals mx plus b example. The weight is the m in front of the x, and the bias is the b in that early like formula, right? So as you can see, we started out in the region of red, which means, well, if I want to go into the region of the lowest error, I need to essentially reduce my weight, maybe move it from 2 to 0, but also increase my bias, right? If I started at the top red corner, then I need to increase my bias to maybe like somewhere past 0, right? So now we're done observing what's happening with this little ball moving in the parameter space and also moving along the air surface. Then let's talk about what is actually happening to the prediction, right? So on the left-hand side, there's 4 data points that are red, and then we're seeing this line, or not line. Well, it is a line. It's just not a straight line. As it gets lower in the air surface, actually fit the data better, right? So this is actually what's happening over and over and over and over again under the hood in your neural network, right? So learning rate is actually how big of a step you take in whatever direction if you were to hit pause on this animation at any point, right? So if we kind of like started where the, in the kind of the red and orange region, let's just say we stop in the very top corner, and let's say, you imagine yourself standing on this mountaintop right there, right? You're probably like, okay, I want to pick the steepest direction to get to the lowest point. And therefore I need to maybe move a little bit towards like the 0, -2, the kind of the -2 kind of like coordinates, right? So, but then how big of a step do you take is what the learning rate controls. So now, with that said, and the last piece of this before we can like discuss deep learning and you having some kind of like ability to maybe like grok this if this is new to you is okay. So we just said what neural networks are doing are taking small steps in the right direction. Then how do we know what is the right direction? So to do that, we basically need to calculate gradients, which is something, well, in mathematics is actually partial differentiation, and this is how you figure out what is the best direction, right? So all this visualization is showing you is that the arrow is pointing towards where the dot is contacting the surface, and it's always pointing to the direction that is has the like biggest slope, right? So partial differentiation. If at this point you're like very confused, like, oh, that looks like a simple surface to do this on. What if like my air surface looks like this? At that point, I also start crying, and this is why you have things like TensorFlow, right? It's done automatically for you. So with that said, let's go back to the original content, and then I will check for errors as well, or sorry, check for questions as well. Okay, cool. Do we have any questions so far about that stuff? And before I go back to the slides, maybe like email me after, because the deck is not updated. There are maybe things that are like little outside of the well, it's not incorrect, but it's probably like stuff from maybe like a year or two ago. Okay, so we were actually just talking about the learning rate, right? So now this graph will start to make sense to you, hopefully. Okay, so what is happening here, right? This is showing you if you have a specific like air surface on top, if you choose a learning rate that's too high or too low, what would happen to kind of where your loss is, right? So in the first example, your learning rate is too slow. That is like, okay, we figured out exactly what is the right direction to go into, but we're taking like baby steps. Like if you were dropped on top of a mountain, your job is to get down to the very, very bottom, or else a bear is going to eat you. You're going to be taking pretty big steps, right? You don't want to be like, walking like a 2-year-old or anything like that. So then you're like, great, let's take giant steps, right? What happens then? You can actually end up in a situation where maybe your local slope is like, oh, the best direction to go down is actually towards the east. But what you don't see is that after like the next hill, there's actually a giant cliff. So you cannot actually go down that cliff. Or maybe there's a mountain right behind you, and the loss actually goes up if you keep heading east, right? So if you were to take like 5 steps towards the east, yes, you're reducing your error, you're learning better parameters, your neural network's actually learning things. But if you take like a 500-kilometer step to the east, you may actually end up on a higher mountain, or in machine learning, like a parameter space with higher loss, right? So that's what happens when your learning rate is too high. Now, when you're actually doing training, you're looking at your loss graph, right? as you run different like training kind of like experiments, different learning rates, and this is a hyperparameter that we have to tune. If your loss immediately drops and takes off, yeah, your learning rate is too high. It's probably doing what's happening in the force image, right? It just keeps bouncing back and forth because it's taking too big a step, and it just keeps exploding. So that's definitely not good. And then you will have a learning rate, which is the blue line, which is kind of like very, very, very like slowly decreasing. It is decreasing, so it's learning, but you are essentially taking like half a step when you can be taking one step. So you're being too conservative, and it's not efficient, right? So what we want is a good learning rate, where it is the green one. So then the question is like, what's happening with the red learning rate, right? What happens was that's actually the scenario in the third graph on top, right? Like as you get closer to your optimal kind of like parameter area, the little valleys may get very narrow, right? So if your learning rate is too high, if you go like 2 steps to the east, you may overstep the like tiny little hole that will drop you all the way to the bottom of the mountain. Maybe there's like a cave or something, and then you take a step to the left, and then you're like, okay, I went past it. Take a step to the right, I went past it again, right? So in that case, what you will see is that you will learn, your model will have a decreasing kind of like loss, but it plateaus at a certain point, right? And if you're like, this model is like powerful enough, I tried it, it remembered the small data set I give it, why is it not doing better than I expect? Well, then you may have a too high learning rate for that region, and this is why you can use a learning rate schedule or slowly decrease learning rate as you progress in training, right? So the other thing I should talk about while we're looking at this, because these are pretty much all the possible scenarios of your learning rate going wrong. If you landed in a pit and it is actually not the best place to be, like you're landing in a cave, but this cave is not at the bottom of the mountain, there is a cyclical learning rate strategy you can use. What does that do? It basically means that if you got maybe like a bottom of a well, or you landed in a pit, occasionally, and you're making some small steps, like 2 meter jumps, right? It may not be enough for you to jump out of that hole and then be able to continue to navigate into a region of lower error or a better parameter space. So once in a while, it's gonna say, you know what? Like I've been trying to learn things. I've been trying to descend this mountain for a long time now. It's not going anywhere. How about I use a super large learning rate once in a while? That may be the kind of the opportunity you need to get booted out of that local minima, right? So it's not a global best option, but it's it's an okay-ish option in that little space that you have explored. So hopefully that makes sense for people. Okay, cool. Oh yeah, that's right. I mean, I'm not sharing the screen, so I'm just kind of like putting the links in there. Oh, actually, that might be a bad move because I know the stuff in the links are not shared. Yeah, sorry about that. Next time I'll actually share my screen. Okay, so I will share my screen now. With the actual image. Yeah. Okay, I'll just share this thing overall then. Okay, so distributed training approaches. Back to the. Okay, so I kind of preemptively mentioned like already why this is important, and it has a lot to do with the compute required in deep learning, right? Which is why I thought like it may be a good idea to go over that real quick. So here are some of the strategies that we have for doing distributed training. First of all, the two that's popularly implemented and frequently used is called async parameter server, or PS, parameter server, or sync all reduce. There are many different variety of sync all reduce. Some are ring all reduce, some are tree all reduce, but they follow a similar principle, right? So what is distributed training designed to do? So as you know, before we had large models, we had big data. So sometimes your data is too big to kind of like fit on the device memory, or it's too compute intensive. You kind of need to kind of like distribute resources, right? So normally that's not a big deal because you can easily distribute resources. But as we kind of like got to bigger models, it takes more memory to keep the weights. And also, this is also why if you ever use like training on the free Colab tier, you probably ran out of memory before you ran out of like compute, right? When I do like random prototyping, experimentation, all of that, sometimes I just kick off a Colab instance with a TPU or GPU, right? And when I come back to it and it's failed, usually it's running out of memory and not something else. And by the way, I always do my like early prototyping on Colab because it's just a lot easier. Until I'm sure the model's like learning, doing the right thing, it has probably enough capacity. It doesn't have the property of like bad learning rate. Then that's when I kind of like kick it off into a actual server and like do the proper training. I do a bunch of like test runs before, so I'm not sitting there having coffee, chilling with people, and then go back to it and find my model still sad. And I waste a bunch of compute, right? Okay, so back to this. What does the async parameter server look like? So this is a strategy for kind of like distributing data and keeping the same like a similar set of model weights, right? So you have a few parameter servers. These are the things that are in charge of like what the weights in the models are, right? So the W matrix times X or the M in the MX plus B equals Y example. And then you have these kind of like compute units called workers, right? So workers have probably like slightly different data. So what happens is in the first step, the workers will request the parameters or will receive the parameters from the parameter server. And then based on its data, on its kind of like each worker, it will basically say, okay, I did a few steps of like gradient descent, or I did some computation. This is my updated weights. And then in this stage, this is gonna get sent back to both parameter servers, right? Why is it a good idea to have two parameter server? Well, if your one goes down, then that's bad news for everybody. So because we are sending weights back and forth like this, what ends up happening is that the workers may kind of some are slower, some are faster, some has more data, some has less data, some might be like IoT devices, maybe it's like smartwatch, some might be a compute. So they will have different properties. And because everyone is getting the same version of the weights, and then everyone needs to finish the update and then tell the parameter server, hey, I'm done, my first update. Is everybody else done? If you have a very slow kind of a compute unit, if one's like dropped out for whatever reason, if one server center catches on fire or whatever, then you may be waiting for that slow worker for like a very, very long time, right? So this is why it's like not super ideal for those situations. So then this is why we have a new architecture called sync all reduce. So what does this do? Basically, this removes the need to have a central parameter server. As you can see, there's no PS anymore. And then what happens is each compute unit, each of the workers has a data set and maybe different data sets, and they're just sending the weights to each other, right? They're just sending the weights always to each other. And because of this, you actually have less need to like make sure each of the step is done before you do the next iteration, right? So that is much more favorable in many ways. So that is kind of the main difference. So when should you use which? That is a really good that is kind of the key thing we're trying to figure out here, right? So if you have like a lot of unreliable workers, a lot of like kind of like not uniform workers, then async parameter server will typically work better for you. But it is a more mature approach, but there's a lot of communication going back and forth, right? So async all reduce is better if you have multiple kind of devices on one communication, because now the constraint is kind of like compute power, right? So if you have a machine with multiple GPUs, then sync all reduce will be better for you as a distribution strategy. Okay, so let's look at see if there's any. Oh yeah, my Ethereum is definitely dropping. As usual. Is there any questions about this so far, or? Okay. Decentralized distributed model training. Ooh, Terrence, good questions. Okay, so let me maybe would people be interested in hearing about federated learning and how that is different than distributed training? So thumbs up, thumbs down on that topic. If only Terrence is interested, we don't need to go into that. Okay, not hearing a lot of upvotes. Only 3 votes. That's not enough data. I am probably gonna skip it. Okay, cool. And if there's time, we'll go back to it. We'll skip it for now. It's alright. Well, I think we will get to it. And how much time do we have left? Because I know like I had a lot of struggles and we're joining a little late, or I joined a little late. Yeah.
Well, we're until 5:30, but we can stay over if people want. There is no hard stop if you're available.
Okay. Yep. So I can down to like another like 20 minutes after. But let me actually go through the rest of the content real quick, if that's okay. Can't drop. That's actually pretty good. Okay, model explainability. Oops, I need to share my slides. Oh, I am sharing my slides. Great. Okay, so super important because a lot of the times when you have a machine learning model that performs better, right? You hear these cases like, oh yeah, like this model performed better than panel of like X many experts. That's great, but why is it right? Until you know why it's making certain decisions, I don't believe this model can be trusted to make decisions by itself, right? And therefore, I would love it if ML could like automate a lot of my like daily tasks. So I would love to have model explainability. So you can do a lot of work for me, but until then, I can't fully trust it. So this is actually basically what model explainability is about, right? It's just like, okay, so this is your conclusion, machine learning model. Can you tell me why, right? What were the key factors that made you decide this is the case? If I'm kind of like, looking to buy a car, I want something that's like fuel efficient. And if it's not fuel efficient, or if it's not hybrid or electric, then I'm not buying that car. So that's a bad car for me, right? So I can explain that to you. But models, we're still working on it. Gradient-based attribution. So this is very popular. It works for a lot of different kind of like inputs and different models. So it's pretty nice. I think the best way to I will go over this formula, but the best way to describe this is actually like through like a visual example, right? So what you're saying is that for each feature X, right? And remember, in machine learning, X usually means data. If you see X subscript I, it means that's a specific data point. It may be like the 20th data point, right? So what is the gradient in terms of Y? Like, what's the change in Y, which is the prediction result over the changing X, right? So this is like a very simple thing this technique is actually doing. So it's basically doing linear extrapolation. Well, actually, mostly linear interpolation. Maybe we'll do extrapolation. So let's look at an example of what it's actually doing here, right? Okay, so this is a example of like classifying a image, right? I think this is probably from Cypher 10. There's 10 different categories, and I'll tell you now, I didn't know what this was before until I looked very closely at the very top right-hand image. It's actually like a water spraying boat. Maybe it's like a firefighting boat for maybe other boats. So now we're trying to figure out, okay, like you either classify this correctly or not correctly, and in this case it did. What makes you believe this is a water boat? So then you're asking it, okay, so show me what pixels you're most intensely activating that's causing your activations that led to this result, right? So when you look at the two bottom like I guess green bars, this is actually in the steps of time or in the sequence of time, right? So the x-axis also basically you can think of it as the x-axis in the graph also applies to the green bars below. So you start with a uninformative prior. or something that's basically like has no information, right? So you can use a image of the same size that's all black pixels or all white pixels. I was like, well, why black and why not white? To me, like a white image has no information either, right? Well, black is actually 000, I believe, and white is like full RGB for every color, so that's like 365 or something for all three of them. So I guess black is a better uninformative prior for this case, right? So what you're basically saying is, okay, for each pixel, or for you, you can just think about like each little grid on the image, right? If I go from a completely uninformed image of all black pixels with no information to its final form, which is the photo we see on the top green bar on the right hand side, like what is being activated in the model, when do we have the biggest gradient, right? And so you can look at the graph on top and see, okay, so it kind of flattened out after maybe like the first quarter, but there's definitely a definitive point where it became very, very certain that this is a water boat, right? By the way, the y-axis of the score is a probability score of like how likely is this image to be a water spraying boat, right? So it went from like not very sure to like very quickly very sure that this is a water boat, like before it was halfway through training, right? So what you're saying is like, okay, like what was the difference between you being unsure to you being very sure? And let's just use like 50% on the y-axis as a cutoff, right? So you will see what is actually looking at are starting from like, oh, maybe the bridge is important to actually the sprays of the water is the most important part. And then as they progress training even further, it's not really learning anything new, so it became kind of like pixelated general items, right? So hopefully this is making sense. So you're looking at the gradient change. You're like, okay, at which point did you become very certain that this is the such and such, or this is a toxic word? Because this technique also works for large language models. And then you're gradually kind of intensifying the input, and inputs in this case would be each pixel, right? So little grids going from the top left corner, bottom right corner. So once again, when you do this technique, what you end up seeing is that this is a water boat because it's seeing, oh, there's a bridge and there's a bunch of like sprays of water from the middle of the water. So it is a water boat. Cool. So that's that. Let's quickly go over some sample questions, and I'll stay around for another 20 minutes or so to answer any spare, extra topics people are interested in. My apologies for running a little bit overtime on this. So, do we have an answer? You need to write a generic test to verify whether a dense neural network automatically released by your team have sufficient number of parameters to learn the task which they were built. What would you do? So this is the thing I kind of mentioned earlier. How do you know your model has probably enough capacity, right? So I'll give people a little bit of time to answer. Okay, so no peace, please. Nobody's allowed to downvote this one. I want actual answers. What do people think? I should probably put the. Yeah, sorry. I should probably pull the slides up. Okay, so let's hear the votes. And Anna, when you see like more than 10 results, feel free to let me know, and then we can take up the answer. Okay. Cool. I'm seeing a lot of D, so good. I'm maybe helping you cheat a little bit. I did not look at these beforehand, so apologies for that. But basically, it is kind of what we described before, right? So train the model with no regularization. And because it's literally remembering the data, we're not looking at the loss function on the test set. We're looking at the loss function overall. you should expect that it is able to like remember the patterns in the data, right? So first you make sure you can understand the patterns in the data, and then you can regularize it to like make it underfit, right? So that is fine. Okay, and then the next one. So I'm gonna read the question to you. The next question is: you're working for a textile manufacturer and have been asked to build a model to detect and classify fabric defects. You train a machine learning model with higher recall based on high resolution images taken at the end of the production line. You want quality control inspectors to gain trust in your model. What technique should you use to understand the rationale of your classifier? Oh, I think we just went over this. So I'll give everyone like 10 seconds to answer. Please do not say P. Um, yep, E is always a good answer. So this is actually going to be B, right? Because this is a transparency kind of like question. Basically, anytime you hear about trust, is like, okay, like how can I, add some kind of like model explainability? Okay, the next question is: you're working for a large retailer. You want to use machine learning to forecast future sales, leveraging 10 years of historical sales data. The historical data is stored in cloud storage in Avro format. You want to rapidly experiment with all the available data. How should you build and train your model for the sales forecast? Do people have answers? I feel like this question probably like was already used previously. Okay, we have a vote for B. Okay, so I'm gonna wait for more answers. Okay, seeing a couple B's, seeing an A, good stuff. What is Avro format? This is a specific format that Google uses. To be honest, I don't know the exact details. So feel free to look it up. If you want, we can also ask Bard or Palm API. Okay, so I see a lot of B's, and I don't actually think that's the right answer. Yeah, it is not the right answer. So the right answer is A, and I will explain why. Right. So it's a lot of data. You're looking for like quick iteration. Immediately when you see that, I start to think BigQuery, right? Why? Because BigQuery is known to be fast and flexible, experimenting and iterating. That's what BigQuery is like meant to do, right? So there's that. But then let's say I'm not super sure about this. What other information can I gain out of this question, right? You may be like, oh, Maddie, previously you said there's like two CSVs. It's probably CSV. Well, no, it doesn't work in this case. So it's better that you actually learn the material and don't just use like test taking tricks. Why is it not AutoML, right? AutoML is a good way, but it's also like a slightly lazy way. And for the effort you save, it will cost you in compute. So if you have a different way, don't use AutoML, right? AutoML makes a lot of sense for two sets of cases. One, you're a like machine learning isn't your core product. Machine learning isn't your core expertise, but you do want to have a machine learning model. Okay, pay compute, hit AutoML, you will get a decent model, right? So that's great. You don't have to hire an ML engineer, even though you probably should at some point. Then the other case is like you went through a bunch of model iterations, you tested maybe like 3-4 different models. Some are state of the art, some are the most baseline, some are the ones that will perform well and are robust and easy to explain in production, right? And then you're literally at the end of your experimentation, you're like, okay, I wonder what else I can do to squeeze more performance out of this model or to make the accuracy better. Then that's also a good time to run AutoML and actually make it use your models, right? So that's the stage where you do hyperparameter tuning and batch size and figure out the right learning rate and a lot of things like that. So there's that. why do we not want to use the RN or the XGBoost model, right? It's actually simply because RN for this would be like very much overkill. You could probably perform pretty well. It would probably like very much overfit. And then the last one is XGBoost is also probably overkill for this. XGBoost is not known for making like good time series predictions because XGBoost is a tree-based model and it doesn't do well outside of your sample, right? So what it means is that let's say you only have data from a value, like you only have input data from a value of 0 to 100, or from January to March. Now you're in April, and in those cases, the tree-based algorithm don't perform as well for kind of out of a sample generalization kind of things. So that would be the quick take on this one. So Q&A, people are free to drop. Oh, awesome! Avril has schema data. Thank you for finding that out for us. That was a little bit tricky. I'm gonna stop sharing now. So I'm gonna stay on for another 15 minutes or so. Are there things people want to talk about? Or questions in general? No questions? Okay. I guess I get to leave. Okay. Adoni, yes and no. There's actually a existing practice example set of questions out there, so feel free to like look at that one. Awesome. And are there still people interested in federated learning? I can like quickly do a detour on that. So I'm seeing a question about any resources for federated learning. By the way, what we just talked about is not federated learning, it's distributed learning, right? And federated learning is very close, so I want to maybe like take a tangent into that. So the difference between federated learning and distributed learning is that it's how the weights are being sent in the form of updates, right? So example we just had, let's actually like use a very simple like human example, right? So let's say there's a central parameter server and Anna and I both have a like a separate number. That's our data set, right? So let's say my number is 42 and the number is 10, right? So the parameter server will send the initial params to both me and Anna, and then we're gonna look at it and we're like, oh, we're doing graded descent, and 1 is too low, so we need you to increase in size. So maybe Anna move her number to 2, send it back to the server. My number is 42, so maybe I said 8, send it back to the server, right? So then the server will basically compute a aggregate for the parameters and basically like send the weights back to us. So maybe now the new weight is like 5, right? Okay, so we do that again. We'll do that again. Eventually, Anna's gonna be like, you know what? My number's 2, my number's 2, and my number's 2, and eventually I'll say my number's 42, right? And then that's how this process ends up learning kind of in a distributed manner the different numbers. Now, the main difference between federated learning and distributed computing is that in federated learning, we actually do not need to send the weights back and forth. We only send the difference, right? So when the weights first came from the parameter server, in that example, the update for Anna is actually +2. For me, it's +8, right? So we actually don't need to send the number of like 2 and 8. We actually just send the difference back to the server. So why is that important? If you're doing distributed learning, the server basically knows where your data, right, is, and sometimes it doesn't matter. But if you're working kind of like privacy preserving settings, sometimes you don't want the central server to know what your data looks like, right? So one way of doing that is not sending what the weights are, but sending what is the update to the weights. So basically you're saying, hey server, I need the parameters to go up by this much, or I need the parameters to go down by this much. But you never disclose like what your actual data set is, right? So that is the main difference between distributed learning and federated learning. both of these are essentially parallelisms in machine learning, and there's like two main kind of families, right? One's a model parallelism, where if you have a large model, you actually have to split up model weights. Maybe you have the first half of the network on one set of clusters, and then the second is like on the second half, or maybe you can actually split it like horizontally as well, right? So there's federated learning, horizontal federated learning, and also vertical federated learning. So feel free to look into that. And the other way of doing federated learning is actually like, or distributed learning is actually data parallelism, and that means we're gonna split up the data set into different like compute units or different workers, and then they will apply the same model on the different data sets. So that's kind of the key differences. It's very closely related. People frequently get this confused. Because I work on a lot of like federated learning research and open source. It's a good time to kind of like explain the difference. Any other questions? So I saw a question earlier to say if I've taken the CERT exam and what materials were best. I did not do the CERT exam, but I don't expect it to be like insanely difficult if you put in the work, right? Personally, what I think is my strategy is look, if you to be very frank, if you just wanted to pass and get a cert, there's a large number of tests, practice tests that's out there that you can do, and you can train your neural network to actually remember the answers, right? And then you will probably pass on the test. However, I don't actually recommend that because the information you just memorize, you spend all that time. If you don't actually practice it, you won't remember it, right? And this is why it's actually important to do the labs. So I would definitely recommend a combination of both. I would definitely use any sample questions that you can get your hands on. And the way I would use the sample questions that I would go through it blind and basically like do it once and figure out like where I need to review, and then I will kind of like leave it alone for a couple months and then review it all again at the end, right? So that's kind of what I would recommend. In the end, it's okay if you take it too early and you didn't quite make it. Even though the voucher is only good for one shot, you can take the test many times. So that is kind of like what I know about this. Cool. Any other questions? Other than that, I am going to bounce. Okay, legit.
That was so fun and informative. Thank you, Maddie. And train your own neural networks to pass. That makes sense.
I wouldn't
In
recommend that
addition to
because
experience.
your brain is like way more powerful than a neural network. Actually, it is literally the last frontier. Like we still don't know how the brain actually works. So try to do a little better than neural network, because if you can learn to pass a test, I can easily train a neural network to pass the Google Professional ML Engineer test. So then, what is the difference between you and the neural network? Well, hopefully, it hasn't learned to optimize itself better than you can yet. Otherwise, we all maybe need to start picking up hobbies or something.
Well, the issue is that we don't know the inputs from the test because it changes, and it's
Yes, that
I
is
guess
also a
there are
very good
ways
point.
to hack it, but the point is to be able to do this.
Yeah. Also, by the way, I know we're like really like pushing people very hard. We're pressing you really hard to like pass, right? Yeah, that's funny, Henry. Yep, exactly. Like we're pushing you really hard to get the cert. But like whatever skills you learn, you're still closer to being a machine learning engineer, right? Like I would actually focus on knowing how to do things than, oh, I have a cert. Guess what? Like anyone that can read can probably find out the questions, can train their neural network, because we know there's definitely enough capacity to pass the test. But then when the interview happens, or even before you get to the interview, for people who are trying to break into the industry, you're going to need to build portfolio projects. And that's when, the